might as well do something about this. So if anyone watches the stream, thank you for joining in. I'm not so sure yet what the topic is. So we'll wait a little bit. Oh, there is, I just found out there is a new feature in Restream. I'm gonna try something out. I'll just check a change. I'll just use a generic image for now. Let's use this placeholder image that I got. And okay, that seems to work well. Let's crop that thumbnail and let's see, update. Now, for those who are on the stream later, maybe you can tell me if you see a thumbnail, a new thumbnail. If not, it's fine. It's just a test. And we're still waiting, but we are already in the classroom. I think I'm gonna join the classroom as well. I haven't joined the classroom yet, have I? Nope, not yet. Might as well go in and let's see if everything's ready. So while we are waiting, I'm just gonna go set up the board right away. Let's go to the board. Okay, there we go. Okay, so while we're waiting, we are loading everything we need to load, including the classroom. Right now, I think I'm having some issues with connecting to the classroom, but I'm not having any issues with the drop frames right now, I think. Okay, we've been on the stream for 6 minutes and we still haven't gotten anything ready. Okay, I think I'll join the classroom again. Hold on. So while we're doing that, yes, exam season's really close. That's for a lot of international examinations. Well, not even just that's even locals wherever you are in the world, right? So I'm pretty sure that in the US and in a lot of countries here in Asia, yes, I'm in Asia for those who don't know, yes, schools tend to end around May or early June and start again in July. Okay, something's wrong here because apparently I'm loading everything properly except the classroom. Okay, let's check it out again. Yeah, this is my third attempt to join the classroom. I'll send a quick message here. Oh, okay, so while we're waiting for the student and me, I'm trying to get in as well. Okay. Now let me change that real quick. Where's the circle? There we go. Ah, that's why it's still tiny. Well, let's make it small, but let's make it fit here. Right, there we go. We have a background now. That's more interesting, I think. So let's, even though it's a tiny one, but let's see. Yep, looks better. see a background. Ah, still unable to load the classroom. Hold on. Let's do it again. Okay, if this doesn't work, I'll try a different browser just in case that it's a browser issue. And I'm getting ready with my other browser. Oh, there we go. Yes, it's working now. Alright, so never mind that. Let's close that. Excuse me. Let me send a message. Everything's fine on my side now. Okay. Alright. For some of you, if you're in the Western Hemisphere at the moment, it's Happy Pi Day today. It was Pi Day here in Asia. So I was just looking at a few things. I was actually watching a few videos from math channels on YouTube, mostly about pi being pi and therefore how to calculate it. Ah, they come up with these new things every day. All right, and yeah, very interesting stuff, honestly. But I sure would like to come up with my own soon. So, but I like pie, both the number and the food. All right, so okay, I think I'm already in the classroom. Yes, I'm already in the classroom, and I got the photos. Okay, let's open them up. And I'm also gonna share my screen there. All right, I have the questions ready. Let's see what the questions are about. 7 questions in total for today. Let's see what they're about. Okay. Ah, right on cue. I was just studying this to make sure that I have refreshed myself. And we're doing some relativity, I think. Yes. Yes, relativity. Okay, show. Okay, let's take a look. Angular momentum. Okay, we have that. Relativistic speeds, relativistic speeds. Yes, we have relativity today, and I think we're gonna go through how it all works. But there is a question here that isn't quite about relativity yet. It's about angular momentum. I'll just post a question on the board now. I think you should be able to see that. And here she is. Hi, Gita.
Well, hi, sorry I'm late.
No worries about it. Uh, what happened? Like, what happened to your computer?
It's still not working. It glitched off, so
I
I'm on my
see.
phone right now.
All right. Well, I still got that question, so we're good, right?
Yeah.
Okay. Um. Okay. Where were we? So let's start off with this question now. Yeah. Um. Okay. All right.
Okay.
Go
Most
ahead.
of the questions are special relativity, and I skipped a couple of lessons, so I kind of have no idea what's going on.
Yes.
So
So
could we do?
I think I
Yeah.
have an idea that we need to go through the whole thing either way, whether you skipped it or not. I think you really need to go through the whole thing again, right?
Yeah.
Okay, so don't worry
Okay.
about
Yeah.
it. I am ready for it. In fact, just so you know, I was thinking about how to solve more complicated problems than what you have with relativity.
Hmm.
So right on cue. All right. So, oh, okay. So let's start with this question first. The angular momentum question. Okay. First of all, we have to know this is a little bit tricky because of the fact that we have to make it into a black hole. We have to make Earth into a black hole in this problem, right? So first
Yeah.
of all, we need to find the angular momentum of the Earth, okay? Whether it's a black hole or not, okay? Now specifically, let's call it the initial angular momentum, okay? Um, well, properly, this is supposed to be okay, hold on. MVR, okay? Where V is the rotational velocity, right? But remember, this particular formula, works if if it's moving, if this is the mass and the mass is concentrated here, and it's going around like this. Okay, so this particular equation doesn't really work. So what we can do instead is we can use the other form. So um, we can use the other form here, which is equal where angular momentum is equal to I, is it IR? R squared. Okay, IR squared. Here's the thing though. This is important. The part here where it says we're assuming that it's a solid homogeneous sphere. This is important. Okay, because okay, I think I better change that. There is something wrong with what I wrote. Should be I omega. Should just be I omega. Okay, omega would be the rotational velocity. Okay, so and omega. So I would be the moment of inertia, and then omega is the angular momentum, angular velocity. And this one is that's just basically equal to 2 pi over the period, right? Okay. Now here's the thing. Since it says there that there's the angular momentum of the earth and you're assuming that it's a solid homogeneous sphere, um you can just take a look at um list of formulas, okay? Okay. There's always a table of the angular, or rather the moment of inertia for particular shapes. It's gonna be important here, okay? So I'm still looking for the actual thing. I think this is gonna work. uh okay, hold on, I'm looking for a good list that we can just copy here. Okay.
Okay.
Solid sphere, is this it? Yep, I think I got an image. I'll just paste it here. Here we go. Okay, Byju's, thank you for the image. It's useful. This is what we will use. Okay, there are other tables that show us what the equations are for particular shapes. Since we're using a solid homogeneous sphere, we're gonna use this formula here. Okay.
Do you know if these are in the formula booklet?
I'm not so sure if it's in the formula booklet, but from what I understand, if it's not in the formula booklet and it's a bunch of equations like these, this will be given to you. I've never seen any particular problem where you have to memorize any of these.
All right.
Okay, all right. So anyway, for now, we're gonna use this. So we're now gonna put that into the formula. So L would be equal to 2/5 m r squared times 2 pi over t, right? The t here, I'll just put 24 hours. Okay, I'm not gonna convert that into seconds just yet. So that's the initial. Okay, right.
Mhm.
Now the second part is knowing when the Earth actually becomes a black hole. This is okay. So the second part is what's the radius of a black hole? What's r for a black hole with the mass of the Earth? So that's the second part. Okay. I don't think you're given the equation anywhere in IB, so that means we can actually look for that formula. Um, I just gotta ask, you've not learned about the thing called this. Okay, I think I misspelled.
Mhm.
SCH, okay? Schwartz shield radius. You've not learned this, I would presume.
Uh, I don't think so.
All right. Now, just so you know, this is the radius of a black hole. Once you know the mass of something, you can. This is the maximum radius of a black hole. Okay,
Mhm.
given the mass of something. So, like I said, since I don't believe you've learned this, we're just gonna cheat and just check on the internet what the formula for that is. Okay. Uh,
Yeah.
okay. So formula for Schwartz shield radius. Schwartz shield radius. All right. Here's the thing. Now, I've looked at this, and the Schwarzschild radius by formula is 2 big G big M over C squared. Okay, we know the mass of the Earth, so we can just put it here, right? Okay, now here's
And
the
C?
sorry, C is the speed of light.
Okay.
Speed of light. All right. So what we're gonna do now is we're not going to do anything with the symbols. We're keeping the symbols first. Okay. So the final angular momentum, we're still gonna do the same thing, I omega. Okay. But now we're gonna change our radius. Okay. So what's our new? We're still gonna use the 2/5 m r squared, right?
Yeah.
So we're still gonna use that m. The mass is still the same, so it's still m. The r now is this though, so we're gonna square that. We'll just put that in bracket. 2g big M over c squared, right? Times our uh or our new omega, 2 pi all over the new period f. Okay. All right. Now what do we do? We're gonna equate those two things. So once we equate them, we can see what cancels out already, right? What so if Li equals Lf, because in momentum, whether it's linear or rotational momentum or angular momentum, conservation is key. Whatever the momentum is at the beginning, you should have the same momentum at the end. So they should equate each other. Okay? So we can see what cancels out already. 2/5 cancels out. One of the big M's cancels out, right? The 2 pi cancels out. So we're left with r squared over 24 hours. So I'll just do the shortcut here now. So it's gonna be r squared over 24 hours. That's gonna be equal to what 2 g big M over c squared times 1 over the final period. Okay. All right. Then from here, it's just a matter of calculating the actually we don't even need to go to 2 pi over 24 anymore. We just need to go omega because that's the question, right? So we will put uh okay. So what will we erase? I won't erase. I'll erase this now, but I need to put back the 2 pi here. Okay, and that's gonna be omega right there. Then from here, omega f. So that means that omega f will just be uh 2 pi r squared c squared all over uh 2gm times 24 hours. The 2 cancels out. The rest of this we can just calculate, put that in the calculator. Okay. Okay.
Okay.
All right. Any questions for this for this problem here? Okay, you're given the mass and
Uh,
you're given the radius, so plug it in.
yeah. Okay. Okay, I understand.
All right. Again, I just want to say it again. We have to cheat a little bit because we need to know the Schwarzschild radius for a black hole. Okay.
Yeah.
All right. But other than that, it's a well. I think that was a challenge problem when it was given. Okay. All right. So, if that's done, let's go to special relativity. Okay.
Wait, sorry.
Go ahead
For the
first.
answer,
Uh-huh.
the bottom number is 24
24
H.
hours. So
Okay.
we're gonna have to convert this into seconds later on. Okay.
Okay.
All right. So okay. Okay. Anything else? I think that's it. So let's go to special relativity. Okay.
Yep.
Okay. So I think we better not go into the problem straight away. We'll introduce the problems as we get to certain ideas first. Yeah.
Okay.
Okay. Uh. Okay. I just gotta ask: is there anything you understand, like any little bit?
That when someone accelerates,
Okay.
they age slower.
Okay. The aging thing. All right. Okay. So let's start off with the history. Okay. Uh, but first, let me update this. Special relativity.
Yeah, I mean, we looked at like the reference points and things, but I honestly don't really get anything.
Okay. I'm gonna use terms that are a bit more friendly that you would probably be more familiar with. Then we replace those terms slowly with the more technical terms. Okay.
All
All
right.
right. So let's start off with daily experience. Okay. Daily experience. Okay. Now, in daily experiences, let's assume that for now, this is you, this is you, okay, and then this is me. This is a car. Let's just say a car. All right, and this car is moving away from you at 5. We'll use kilometers per hour for now. Okay. Okay. So according this is this. Okay. So let's take a look now at okay from your point of view, from your POV, right? What do you say is happening? The car is moving to the right, right?
Yeah, away from me.
By how fast? At
5 kilometers per hour.
okay, 5 kilometers per hour, right? Now, let's change the point of view now. The cars. Let's take a look at the car's point of view. What is happening according to the car's point of view? Remember, in this case, we're simplifying everything. It's just you and the car. There are no roads. There are no trees. The earth isn't even there. It's just you and the car. Okay?
Right.
So, from the car's point of view, what is happening? Is it moving or are you moving?
It looks like I'm moving
Okay,
at 5 kilometers.
so you're moving 5 kilometers per hour, correct? But which direction?
To the left.
To the left. Okay. Per hour to the left. Okay. So this is the daily experience, and we always see this. And this exactly is one more thing before we go here. let's put you that you are moving at 0 kilometers per hour, right? Or whatever unit it is. Okay. So you will notice here that in this case, both are moving at a uniform speed or constant speed. Okay.
Mm-hmm.
In other words, this particular motion, let's now turn this into the technical language. Okay. When the two objects are moving at a uniform speed relative to each other, you call these inertial reference frames. Okay.
Yeah.
All right. So far, so this would be an inertial reference frame. Okay. Now I'm gonna.
That's
Sorry. Go ahead.
that's when it depends on the viewpoint and
Yeah.
how
Now,
we are moving.
yes, exactly. Both of these are inertial reference frames. Okay. Now, in the absence of any other object to compare to, both views are valid, right? It's you're moving according to the car's point of view, but the car is moving according to you, and they're equally valid. Okay.
Mm-hmm.
So that's the important thing about reference frames, inertial reference frames to be more specific. Inertial reference frames are equally valid points of view. Okay?
Okay.
So in other words, you cannot say I'm right and he's wrong, but the car cannot also say the same thing, that the car is right but you're wrong. Okay? Points of view.
Yeah.
All right. So okay, that's a daily experience, and I think that simplifies everything, in especially this term, inertial reference frames, right? Okay.
Yes.
But the problem here is, let's before we go to the problem, let's now introduce a third object. Okay. Now, let's now introduce a third object. So first of all, there's you again. So let's say that's you, and then let's say that this is the car, and let's still keep it. Let's make it now with. Let's put it now in meters per second. So this would be around 40 meters. Is that correct? 20 meters per second. Let's say 20 meters per second for now. Okay. Right? And then there is a third object. Let's use a different color, green. Okay. Now, let's say that there's a cat. This is a cat. And this cat is moving this way to the right at 1 meter per second. Okay. This is all from the perspective of a so-called outsider. Okay. But for now, we will ignore who the outsider is. Okay. Now, let's take a look at this. We are gonna ignore the cat's reference frame. We're just gonna look at you and the car. Okay. According to you, this one should be the. Actually, no. I'll change the cat to something else because it's too similar to a car. Let's say that this is a. Let's say
Dog.
okay. Let's just go for a dog. Okay. According to you, let's go back now. According to you, the car is moving at 20 meters per second left, right?
Yeah.
Now, and also according to the car, you are moving 20 meters per second to the left, to the right. Sorry, this is left. The other one is right. Okay. Right. So let's change that a bit. Okay. Now, the third question now is, how about the cat? According to you, how far is the cat moving?
It's not moving.
According to you. So here, remember the. Sorry, not the cat, the dog. There.
But I'm stationary.
Yeah, you're stationary, but look, the dog is moving at 1 meter per second.
Right. So they're moving 1 meter per second.
All right. So okay, that's so far again pretty obvious, right? 1 meter per second, right? But according to the car, how fast is the dog moving?
Like 19 meters per second.
Which way?
To the right. Towards the car.
It's towards the car, but the car's also moving away from the dog, right? So think of it as in terms of the distance. Is the distance between the car and the dog increasing or decreasing? So it's increasing in this
s-
case, right?
but they're both moving, so shouldn't it be constant?
All right, so that's a good question. So let's kind of look at this now. I'm gonna stop sharing for now so you can see camera. And let me share this as
Mm,
well. Okay,
yeah.
so let's do it like this with my hands, okay? So this is the dog moving this way, right? This is the car moving this way. So if the car's moving like this, the car's moving faster than the dog, right? So it's gonna be like that. So what's happening to the distance between them? Let's take it from here.
Increasing.
The distance is increasing between them. So from the from the car's point of view, it seems like the dog is moving away from the car, right?
Yeah.
Okay, so that's why if we go back to the board now, okay, uh, share that again. If we go back to the board, so this is why what we mean by the dog is moving 19 meters per second, but this time to the left, because the distance between the car and the dog are increasing, so the dog is moving away. So it has to be moving to the left. Okay, but the 19, I think it's easy where we got that 19, right?
Yeah.
Where'd we get 19? It's just that, subtracting the velocities. Okay, all right. So far, okay, so far so good. Let's see if there's a question similar to that. Not yet. All of these are with special relativity. Okay, now what we've done so far, all of these things that we've done so far, this is not the complete thing, but this is under Galilean relativity.
Yeah.
Okay,
And sorry,
go ahead.
according to the dog, how fast is the car moving?
Okay, so let's take a look at that now. So we can do that. So according to the dog, the car is moving how fast now? So you can do two
21.
things. Okay. Okay. Think about it this way again. Is the dog getting closer or farther from the car?
From his perspective,
Yeah.
close. Uh,
Remember, the car's still
well, we
moving
said
faster, right?
yeah, but the dog is still actually going towards the
Okay.
car.
That's correct. It's still moving. The car is still moving to the right. Okay? Correct. But the speed is still 19 meters per second.
Yeah.
Okay? Now, okay, this is the next thing we're gonna go through before we move on to special relativity. Okay? But according to the dog, you are moving 1 meter per second to the left. Okay? So that's the point. These are the reference frames: the car, the dog, and you. Okay. All right. The one thing now that we need to go into here for Galilean relativity is that the relative velocity, and now we're not gonna use speed in this case. We really need to use velocity for this definition. Okay. This is gonna be the velocity, one velocity minus the other velocity. Okay. Uh Okay, which velocity do we look at? Do we do first? We're always gonna subtract the uh the the moving thing. Okay, so let's put that in quotes: mover over observer. Okay, again, you subtract their velocities and not their speeds. In other words, you still have to take into account their directions. Okay, so this is why the dog is moving 19 meters per second to the left. If we put this with numbers, the dog's velocity, the observer, oh wait, did I do that right? It should be, okay, the car. So in this case, it's the car that's the observer, right?
Yeah.
Okay, so we're gonna subtract, so the velocity of the dog minus the velocity of the car. That's the relative velocity, okay? So
Yeah.
our,
Okay.
okay, so this is gonna become 1 minus 20, okay? So
Yeah.
it becomes so that becomes negative 19, and the negative indicates it's going to the left. Okay. All right.
Okay.
Okay. All right. So let's go back now. So anyway, that's for Galilean relativity, we don't really need to go into the intricate details yet unless you've done that before. But for now, we'll skip the rest of it. Let's go straight into special relativity. Okay? Because here's the thing about relativity and what Einstein discovered. Okay? Um, if we extend this idea of Galilean relativity with light, so what if the dog was turned into a light beam? Okay? So in other words, let's do that again. That's you. And then the car is here. And then let's make it move at 10 kilometers per second. And for now, let's say that light, okay, let's say that light is some value. Let's make it easier to deal with. Let's say that the speed of light is, let's put that in quotes, 100 meters per second. What did I say? Kilometers there. Okay, it's not the real value, but it's for illustration purposes. Okay. All
Okay.
right. Now, in this illustration, let's do the same thing again. According to your inertial reference frame, okay, we'll use the term now inertial reference frame. According to you, the car is moving at how? Let's just go straight to the point here, 10 meters per second, right? And then the light is moving at 100 meters per second. Okay.
Yeah.
Now, here's the weird thing about light. According to Galilean relativity, so from the car's initial reference frame, you are moving 10 meters to the left, right? And at 10 meters should be moving. Again, you subtract the mover from the observer's speeds, right? So
100 minus
okay.
10.
Yeah. So mover minus observer. So that's gonna be 100 minus 10. So again, for illustration purposes, that's gonna give you 90 meters per second, right? So the light is moving at 90 meters per second to the right. Okay. Okay. Here's be quick. Be quick. Say hi. I'm using it later. Later, huh? All right. Say hi now before we continue.
Hi.
Hi.
All right. Okay. She said hi already.
Bye. See you next year. Don't let the science bugs bye.
Okay. All right. Now, the weird thing about relativity, let's go back to that, okay? The weird thing about relativity is this is expected according to Galilean, right? Okay.
Yeah.
But experiment after experiment after experiment have shown that this is not the case. Well, not the whole thing. This still kind of works.
Oh no.
This is still kind of works. Kind of works. Okay. But definitely not that. What was always observed is that light. So the observation is that the light also travels at 100 meters per second to the right. Again, with the pretend value for the speed of light. Okay. Of course, if we use this actual value of the speed of light, then that means we're gonna have to change that value to the actual value, 3 times 10 to the 8, right?
Yeah.
Okay. But okay, this is the
So,
observation.
in reality, the car sees the light moving 100.
Yeah. So the car will still see the light moving at 100 meters per second. Again, from this example. Okay. Now, that's a bit strange if you think about it. Why does light not obey Galilean relativity? Everything else that we know of obeys Galilean relativity, but not light. So, of course, I'm not going through the rest of the experiments and observations, but we're going straight to what Einstein did. Okay? Okay? So, Einstein said something. really simple but very profound. He claimed that, okay, speed of light is the same for everything. Light is the same for everybody. And by everybody, he meant at initially all reference frames. This includes non-inertial reference frames. But we'll get to what non-inertial are when we get to general relativity. Okay? So far, for special relativity, we're just going to deal with inertial reference frames. Okay? So
Okay.
for all reference frames, the speed of light is the same. In vacuum, to be more specific. Okay? Okay. Now, since he said this and he postulated this, there's another thing he said before he went on to prove that relativity works. Okay, so that's the first one. Actually, this is the second claim. Okay, his first claim that is that all inertial reference frames are equally valid, which is what we've established earlier. Okay. Okay, but that means one thing. If both we can do the calculations later, but basically with these two assumptions, basically what he came up with is that if light is constant for all inertial reference frames, then that means if the car is moving at 10 meters per second away from you, you are not moving from the car. Or well, you're still moving from 10 meters per second away from the car. But the dog has different speeds according to you, according to either of you. But the light will have the same speeds.
Is this still when the dog is alive?
No, this is now the dog is the dog. Okay.
Okay.
All right. So, but we'll get to what that. We'll get to more specific examples in a while. Okay. So these are the conditions for special relativity. Relativity. Okay. Now, what there has been somebody else before Einstein who came up with a set of equations, and it's actually his set of equations that we use a lot in special relativity. Okay, you may have heard of the name. You probably heard of Lorentz transformations or the Lorentz factor, or let's use the word transformations for now. Okay, if you've not heard of this, have you heard of this yet? Not yet. Oh, by the way, since we started a bit late, is it okay we extend a little bit? Just to know.
Yeah, if you're available.
Yeah, sure, no worries. Okay, let's do that then. Okay, for the Lorentz transformation, there is this factor gamma. This is the Lorentz factor. Okay, and this Lorentz factor, this is equal to 1 minus v squared over c squared, square root. And then I missed something. That's 1 over. Okay, so 1 over square root of 1 minus v squared over c squared. Okay, now okay, this factor will basically tell us how much something will either will be affected by how fast it is. Okay, now that's the first part about this, and then the second thing we need to know is what's called the proper time and the proper length. Okay, now proper time and proper length, the word proper here refers to one thing. Okay, these values, these are the values according to the stationary observer. I'm gonna put the stationary in quotes. Okay, observer. Okay, now of course you can select which one is stationary, which one of the two observers is stationary. Okay, but having said that, once you've determined which one is the stationary observer, we can assign the proper time and the proper length for it. Okay, and then the final thing we need to do here is this. Let's put prime. Okay, t prime and l prime. Okay, This is basically just this is the dilated time. Okay. In other words, for the moving one, for the moving observer, time kind of moves more slowly. Okay, and this is gonna be equal to time over gamma. Okay, and this other one, this is the contracted length. This is just the length. This is time here, and this is gonna be L here. Okay, this is gonna be L gamma. Okay, uh,
Does it change?
yes, it
I
changes.
mean, yeah, actually.
Okay, hold on. Let me double check that. It's gonna be a fraction, so the square is a fraction. This fraction, first it's a bigger fraction. Oh, it's the other way around. My mistake. I always confuse these, but it should be like that. Okay.
Okay.
All right. It should be the other way around. Gamma for dilated time and 1 over gamma for contracted length. Now, this again would be the values for the moving observer. Okay. Okay. All right. So we have these equations. There's still something I want to go through, but I think we'll skip that for now. I just want to go through some simple problems now, so we can kind of see what's happening. All right. Let me see if you sent over a problem we can use.
Okay. And sorry, could you repeat one more time what the Lorentz transformation did, because I didn't hear?
Okay, so basically what this does here is, in this case, it's called let's start here, the contracted length. Okay, now what does this mean? For the moving observer, whatever they're both observing, the moving observer will see that thing to be shorter. Okay, because of the gamma, because of the Lorentz factor, the gamma. All right. Similarly, for this, for the moving observer, again, they're observing the same thing. Okay, when they're observing the same thing, the moving observer will say that the time it takes is gonna be longer by this much time, by this much of a factor. Okay. 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 I think it's better understood if I give you the problem now. One of the problems you have here. Yeah. All right.
I think the one with the egg and Dobson.
Yes, the Dobson problem. Yes, that works. Actually, that's a problem I have here right now. Okay.
Okay.
Okay, so while that's loading, let's hold on. It's taking a while. So while that's loading, let's just do it like this. Okay. Suppose SO here will be the observer who is moving according to the diagram, right? And S is the observer who is not moving. Okay. Now, in this case, again, it's still loading. Why is it taking so long? Oh, there we go. Okay. So let's take into account this. We can actually solve this two ways. Okay. Now, in order for us to do this, we will say that S is the stationary observer. Again, we'll just say it like this. Okay, to make it easier for us to see. Yeah. So S0 will be the moving observer, right?
Yeah.
Okay. Now, one more thing. Whenever we're doing relativity, we actually need three things: the two observers and the object. Okay. So we'll call the object the egg. Like, just keep it simple. Keep it the egg for now, right? Actually, before that, okay. So in this case, what's the velocity between them? So what's the velocity of S0 according to S? It's 0.75 c given there, right? So this is relative to S, yeah?
Yeah.
Okay. We can also say that V0 then is equal to negative 0.75 c. This is relative to S0, okay?
Okay.
So specifically, this is S relative to S0, and this is S0 relative to S, okay? All right. But either way, it's gonna. You see that if we only have two things, we don't really run much into a problem because they have the same value. It's just negatives. They're just negatives of each other, right? So when we get to our third, before we go there again, let's go find gamma. What's gamma equal to? Gamma is just 1 over the square root of 1 over v squared over c squared. Okay. We have
Yep.
0.75. 1 over square root of 1 minus 0.75 squared c squared over c squared. The c squared cancels out. What's 0.75 squared? Let's just put that value now in the calculator. Okay.
Wait, sorry. How does
Go
the
ahead.
c squared cancel out?
Oh, because the speed given to us is in terms of c.
Oh, right.
All right. So because it's if it's in terms of c, it's gonna be a lot easier because once it's in terms of c, we just square this value and put it in the equation. The c cancels out afterwards. Okay.
Okay.
So that's gonna be 0.75 squared, right? 0.75 times 0.75, then you subtract 1. Okay. So this is gonna be, take the square root and then flip over. Our gamma is equal to 1.51. Okay. Again, just put this value in the calculator and we'll get that. Now, it doesn't matter. You see, it doesn't matter if we have the negative or the positive value for v because we have to square it. Okay.
Yeah. And they're always gonna be equal but opposite in sign.
Yeah. Yes,
Okay.
that's correct. Okay. But again, that's always the two observers. Okay. So now that we have these, we have the formula for gamma. Let's see if we got it right. Okay. How do we know? Um, before we solve, remember that this is the easiest way to remember it. Time will become longer for the moving observer, but it will become but lengths will become shorter for the moving observer. Okay. All right. But anyway, sorry. Say you have a question. Go ahead.
Length will be shorter, like in terms of the length between them.
Yeah.
The observers.
All right. So basically, if I'm not moving and I see 1 meter, if I have a meter stick that's 1 meter long and I'm not moving, once that meter stick is moving, it's gonna be shorter than a meter.
Okay.
Okay. All right. So okay. So let's take a look at this. Oops. Okay. So all right. The question now is Dobson cooks the egg in 3 minutes. So let's put this here, right? Let's use B. Blue. Okay. Okay. So in this case, who is observing? Where is Dobson? Is Dobson in the? Okay, Dobson is in the S0 or S. It's not so clear on the problem where he is, right?
Yeah.
Okay. Okay. In this case, let's say that Dobson's measures the egg cooking in S0. So it says here in S0 time equals 3 minutes. Okay. There we go. This, once we identify one, we can set this to be our stationary. So for each problem, you can have different stationary reference frames. Okay. All right. Now, the reason for this is because Dobson, the observer, is moving with the egg. Okay.
Yeah.
All right. Now in S, what's gonna be here? The time here. The time, again, it doesn't matter which one is which. You just really have to say which one is the stationary, which one is moving. But once you go to the moving one, it's always gonna be T equals T over gamma. Oh, other way, T gamma. Okay. So all we're gonna do now is put that value in. That's 3 minutes times 1.51 from our calculation earlier, right? So
And do we change the seconds?
we don't. Well, we could actually, but I'm not going to. You don't have to change in
Okay.
seconds actually. Okay. It really depends on the problem, but for this problem we don't have to. So in this case, we just do that 1.51 times 3. We get 4.5 3 minutes. Okay. So so in other words, the egg cooking in S0 will take 4.4.5 minutes from the point of view of S. So let's write that again here. So the egg in S0 takes 3 minutes in SO, but 4.53 minutes in S. Okay, so that's what it means. Now, what if the problem was the other way around? What if we gave the we put the egg in S and then we said it's 3 minutes? It's the exact same solution with the exact same answer. It's just we switch S and S0. Okay?
Wait, sorry. Could you repeat one more time?
Again. So this is okay, so let's go back here. This is the egg cooking in S0, right? It takes 3 minutes.
Yeah.
Then according to S, those 3 minutes in S. Okay? Now, if you cook the egg in S, of course we know that the egg will always cook in 3 minutes, no matter, as long as it's moving with the reference frame it's at, right? So if we put the egg in S, it still takes 3 minutes to cook. Makes sense, right? But but in that case, because the egg is now in S, S is now the stationary observer, because S and the egg are together. Okay? Now, when the egg was being cooked in S0, then S0 is the stationary observer because the S is with SO. The egg is with SO. Are you getting it?
Okay.
Okay. So basically what do you need to look at? Your third object, you have to see which reference frame is it moving with. Okay? Okay. So basically, what if the egg was now in S0? In S. So let's do it the other way. If egg is in S, right?
Mm-hmm.
Is the egg moving relative to, if the egg is in S, is the egg moving relative to S?
No, they're together.
So they're together, so how much time will it take in S? It takes
the same.
Still takes
3
minutes, right?
Okay. Right.
Still takes 3 minutes in S. How much time will it take in according to S0? But minutes in S0.
4.53.
Exactly. Okay. Now, there's one more thing we didn't account for. We didn't account for length yet. This is just time, right? Okay. All right. So we'll stop here. I don't want to stress you right now. I can hear that. I get it's confusing. Yeah. Okay. Just so you know, I first read about relativity when I was 10 years old, I think.
Oh my god.
I didn't understand any of it at that time.
That's quite early to find out about.
Yeah. But once you kind of get the idea of, you have to look at the point of view of the observer, you'll see how to calculate stuff. All right. Okay.
Yeah.
Do you have a meeting tomorrow?
Yes. Are you allowed to move it to 10?
Yeah. Oh yes, that thing. 10 o'clock. We are 6 hours ahead, so that's 4 o'clock here. I think I can do it. I'll move it then.
Okay. Perfect.
All right. Okay. Tomorrow we'll do length. Okay.
All right. Yeah.
Okay.
Okay. Thank you.
Do we one more thing though? Do we actually need to go through how Einstein got these equations, or I have to check the syllabus if we need to go through that. Otherwise, we won't. Okay.
Okay. Only if necessary.
All right. Only if necessary, because I know how stressful this particular topic is. Okay. So don't worry. All right, so we'll continue tomorrow at 10 o'clock your time. Yeah.
Okay.
All
Okay.
right.
Thank you.
Okay, I'll see you tomorrow. Bye bye now. Have a good day.
Bye bye. Have a good day.
All right, and that's the end of that lesson there. Uh, okay, let me see. 4 to 5. Then I have a 5 to 6. I think I'm okay. Yeah, I'm okay with that. So, relativity. It's not that difficult once you get the hang of it. But that's the key thing there. Once you get the hang of it. So you need to practice this a lot in order to actually understand how relativity works. Okay? But always think about it this way. A moving observer, according to you as the stationary observer, will have a shorter length and a longer time measured. Okay? Now, whoever's the stationary or moving observer depends on who you ask, and they're both equally valid. Okay? All right. So, we'll end the stream here. So, before we do, of course, as usual, don't forget to like, share, and subscribe to the channel. We are here on YouTube, Facebook, TikTok, Instagram, on Twitch when we go live. For TikTok and Instagram, of course, I'm gonna go back to posting shorts and schedules for you to browse as content. All right, and of course as notifications for when we go live. So for today, that's it. I hope you learned something, or for anyone who's gonna be watching this soon, hope you learned something. So with that, I bid you all a good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Stay freaky, everybody. Bye bye now.